Hey everyone. This lesson is another one. This is going to assume that you are here and you were present during the class where we organize these snazzy element tiles, okay, where without specific information, we just sort of take a look at their behavior in this imaginary world where elements are named after the seven dwarfs and reindeer and whatnot. And after organizing it, you're able to identify something like this, something like that, or something similar to this, where instead of grouping all of them or writing all the elements according to their atomic number or atomic mass, you saw that the atoms or the elements had repeating properties. So after 5, the sixth one behaved super similarly to the first one. So it sort of made logical sense to group them together. It sort of continued to go in this way until we had columns that behave very similarly. Okay. So with the idea, the whole purpose of that exercise and that entire lesson was to, I guess, solidify that these columns in the modern day periodic table have similar properties and behave similarly in similar environments, right? So all the stuff here, if you remember from our demonstration, lithium, sodium, potassium, they all reacted vigorously with water. And it makes sense. They are all sort of part of the same family. So that's where our lesson begins. I am going to go relatively quickly. So if you need more time, please be comfortable. Feel free to pause the video and catch up. The lesson on Thursday, that is November the 4th, began with me asking everyone to draw a condensed Bohr-Rutherford diagram of every single element up to number 20. So if you think about it, the periodic table looks something like this, right? And you see this sort of jagged little chasm here, and then it goes back. So this part is definitely left blank. And so when we go back to our previous page, you will see that this column and that column are sort of brought together. We're not concerning ourselves with anything down here. We're going to pretend that this part here is just our current periodic table. Okay, and you'll see that there are patterns to this. All right, here we go. Condensed or Rutherford diagram looks like this. You still have to identify how many protons and neutrons there are. So let me tell you right now, for carbon, there are 6 protons and 6 neutrons. And so the condensed Bohr-Rutherford diagram, just to make our lives easier, you're going to draw half of a nucleus. It's sort of like you took a snapshot of a picture of half the nucleus. You got 6 protons and 6 neutrons. And then you're going to draw rings. And instead of drawing electrons as circles, you're just going to write how many electrons should be inside that ring. Okay, so again, this is under the assumption that you have participated in this lesson where we worked on the Bohr-Rutherford diagram, and you did go through the motions and fill that entire chart up, and you know exactly how many electrons are supposed to go where. Okay. So trying this, in the first shell, there's a maximum of 2 electrons. And on the second shell, there will be 4 more electrons left. You don't have to draw them in square brackets. You can always draw them in curved lines as well. I just drew them in square brackets so you don't get confused with the actual nucleus. I would like you to do this. Protons, neutrons, and the number of electrons accordingly in the number of shells for every single one. I'm going to pause here, or you can pause and go ahead. I'm going to do this very, very quickly, so you might want to try that yourself. Go. Let's get started. And somehow between me pausing the video and me restarting the video, I lost my pen. Here it is. Okay. So helium, in case if you wanted a bit of a quick refresher, you need to go to the periodic table to figure out how many protons and therefore how many neutrons you would have. For hydrogen, you would have 1 proton, 0 neutrons. For helium, you would have 2 protons, 2 neutrons. For lithium, 3 protons, 4 neutrons. Beryllium, 4 protons, 5 neutrons. Boron, 5 protons, 6 neutrons. Carbon, 6 protons, 6 neutrons. Nitrogen, 7 protons, 7 neutrons. Oxygen, 8 and 8. Fluorine is 9 and 10. Neon, I believe it's 10 and, oh, it's bad, 10 and 10. Okay, let's continue. This is what I meant by going fast. You'll probably need a little bit more time to do the calculations for how many protons and neutrons there are. But if you looked at the periodic table enough times like I did, you have a general, I guess, good guess of what that might be. 13, I believe that's 14. I could be totally wrong. Yes, it is. Silicon is 14p and 14. Yeah. And just like what I'm doing here, if you're sort of second guessing yourself, I'll go back and check it out. Sulfur is going to be 16 and 16, I believe. Yeah. Chlorine is going to be 17 and 18. Argon is be 18 and 20, I think. No, 18 and 22. Whoops. 18 and 22. Excuse me for that. Can you see it? 18 and 22. And then potassium, 19 and 20. Calcium is 20 and 20. So those are all my nuclei. And then the first one is a 1. Helium is 2. And lithium is going to be 3 because that's how many protons you have. But the first shell only has room for 2. So you have to move on to the next one. 2 and 2. 2 and 3. 2 and 4. 2 and 5. 2 and 6. 2 and 7. 2 and 8. And the second shell is all full. We don't have enough space. So the next element, as much as we want to add our 11th proton in the second shell, there's no space. So we have to move on to the third shell. We've got 2, 8, and 2, 2, 8, and 3, 2, 8, 4, 2, 8, 5, 2, 8, 6, 2, 8, 7, 2, 8, and 8. Lastly, again, so now I have 18 electrons to match the 18 protons. I want to add one more, but there's no space in that third shell right now. And so we have no choice but to move on to the next one. That's a 2, 8, 8, and 2. This is what I meant by drawing it really, really fast. So pause the video and see if you can fill that in before moving on. Okay, from here, again, assuming that you've taken your time to catch up, what do you notice about all the electrons? So again, if you've done this exercise with me, you might have already seen it. Sometimes with the pictures being so small, you may not be able to catch it unless someone prompts you. The question is, what do you notice to be similar between every single column? What are some similarities visually of every single column? I'll give you a second. And I'm hoping that you arrive to the conclusion that in the first column, every single outer shell has 1 in the first column. In the second column, every single outer shell, no matter what's inside, the outermost shell has 2. The outermost shell has 3. The outermost shell has 4. The outermost shell has 5. The outermost shell has 6, 7, and well, 2, 8, 8. But you see that on the outermost shell of the last column, all of it is full. The number is different, I get it, but the shells are full. Coincidence? In fact, that's not the case. The reason why, going back to your activity with organizing the tiles, okay, organizing the Blitzen and Donner and whatever those element tiles, you see that the reason why sodium, which comes after neon, sodium had the same properties as the column 1 was because there was 1 electron that entered the next shell. It was 1 shell, I guess, the outermost shell was 1. And so all of these have very, very similar properties. Hydrogen is a bit of an exception, but anyways, you get the point. And so we see that there is a connection. And that's essentially it. I'm going to start to use this, right, your organization of properties along with our subatomic particles to sort of bring the 2 worlds together and try to explain like the beauty of the periodic table in that way. So let's talk a little bit about some terms that you will need to know. The outermost shell, sort of a mouthful to say it's called outermost shell every single time. We actually give it a scientific word, and I'm going to write it here. I'm going to call this outermost shell is actually called the valence shell. Okay, VALENCE. And the number of electrons that we see, in this case, that would be 2. In that case, that would be 3. In that case, that would be 4. Those are electrons that are found in the valence shell. We call them valence electrons. So creative, right? Valence electrons. Some new terminologies. Okay, so a couple of things I want to mention now. This column 1 has 1 valence. Column 2 has 2 valence. So 1 valence electron, excuse my shorthand, this is E negative for electron. That's 2 valence E's. Here I have 3 valence E's. We have 4 valence E's. We have 5 valence electrons. We have 6 valence electrons. Get the point, 7 valence electrons, and not 8, clearly, but full valence. That's super important, right? A couple of other things that I want to point out as I was talking about this. I alluded to this in previous classes, but take a look at other things that you might have noticed between not columns this time, but how about rows? You may have noticed that every single time we finished a row, we jumped to the next row because we were entering a new shell. If you think about it, all the elements in the first row have 1 shell and it's full here. All the elements have 2 shells in the second row until it's full here, right? Full valence. And so we have to move on. All the elements in the third row have 3 shells and it's full here, and then 4, so on and so forth. So you can say that maximum, at least on Earth, we have 1, 2, 3, 4, 5, 6, 7 rows. You don't have to worry about this. It's 7 rows and therefore 7 shells that we make. Okay, so let's write this down. Okay, so this right there It's the first row, AKA not row, just like how we have these things called, instead of calling it a row, we actually call it the first period, hence the periodic table. Okay, this is the first row, AKA the first period, and it has one shell. This is the second period. It has two shells. This is the third period, therefore 3 shells. This is the fourth period, and therefore 4 shells. I think you get the point. Okay. At this time, you might want to pause just to get your bearings. Make sure you understand everything that we have written, how we filled this graph, how we filled this blank periodic table, and then continue the video. All right, so let's continue. Once you're ready, you can turn to the next page, and we're going to work out some more details of the periodic table. And we're going to go to the main big one. And since we talked about rows as periods 1, 2, 3, 4, we should also talk about columns. We have a specific name for them, not a special name. It's just called groups. Turn page. Let's get the numbers down first. You're going to have periods, of course, right? So the period is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. At this point, you might be wondering, okay, Mr. Kim, before you mentioned how I had to ignore this. What is this column? To save space, this periodic table was sort of fixed this way. This asterisk means that it actually belongs in between BA and HF. And the 2 asterisks here means that it belongs within RA and RF. Okay. Why is it set up this way? Remember, the periodic table was meant to organize our elements based on their properties. So in other words, rubidium, cesium, francium, they all behave similarly, and so they're part of one group or one column. Beryllium, magnesium, calcium, strontium, barium, radium, they all behave very similarly, and so they're in another group. In the same way, these 4 elements, they all behave very similarly. And so it makes sense that they belong in the same column. But with technology, what they noticed was the number of protons in barium was 56. And the next element in that column was 72. Like, where the heck did 57, 58, 59, 60, 61, 62, all the way to 71, where did it go? Well, those elements did exist. In fact, there's 14 here, but they did not match. 57 did not match. 58 did not match. 59 did not match, right? It did not match all these element columns, but we need to place them, right? Because, the order of the number of protons did seem to fit this periodic table. So either we revamp this entire thing and create this like pseudo 2D, 3D periodic table and take the world by storm, or we just simplify our lives and say, you know what, this does exist. But this section, we're going to pretend it's like squeezed inside here. But it helps us understand the general properties and behaviors of all the other elements if I keep the structure. And so it's sort of like we take this, we shrink it in, and we sort of squeeze it inside here. That's why I said you don't really need to concern yourselves with these 2 rows. They're like an alternate universe. Like if you walk into this portal or this vortex or whatever, and you go through the other side, like, yeah. This is where it lives. Okay, so don't worry about that. Just focus on period 1 to 7. All right, so now that we've talked about periods, let's start talking about columns, AKA groups. Now, I might confuse you a little bit because if you go from left to right, clearly it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 columns. But depending on the textbook, some people call this 1, 2, jump, 3, 4, 5, 6, 7, 8, and then this as 3B, 4B, 5B. In other words, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, but like like the alternate 3, 4, 5, 6, 7, 8. I know that sounds confusing, but let me approach it in a different way. For now, let's just pretend that it is group 1, group 2, group 3, group 4, group 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to say 13, 14, 15, 16, 17, and 18. But I'd like you to pay more attention to the last digits of these columns. So it's sort of like saying 1, 2, 3, 4, 5, 6, 7, 8. And there's a reason for that. Okay. Next, what else should I talk about? Oh, you know what? Might as well talk about why. The reason why I want you to focus on the last digit here is because if you recall from our previous exercise, how many, so this is boron, right? This is, that boron is up top and boron is up here. How many electrons how many valence electrons did boron have? 3. Group 3. How many valence electrons did carbon have? 4. Group 4. How many valence electrons did nitrogen have? 5. 5. I think you get the point. Then we go all the way down to neon. How many valence electrons does neon have? 8. Perfect. I know helium is an exception, but I'm pretty sure you can just memorize that helium has 2 on the outer shell. That's essentially why some textbooks just say 1, 2, 3, 4, 5, 6, 7, 8, especially lower grades. But I think you can handle this. So just 1 to 18, focus on the first digits to give you a hint of how many valence electrons there are. Moving on. Now that we've created this grid, right? 1, 2, 3, 4, 5, 6, 7, and 1 to 18. You can sort of use this like battleship and say 4, 3, bam, like 5, 7, bam. Anyways, now we can start talking about the actual properties and what you see in the periodic table. What I'd like you to do is take a highlighter, use blue, actually, sure, I'll use green. I want to draw a staircase. Please draw a staircase from underneath boron, and then down, right, down, right, down, right, down, right, a regular staircase. And you can pause the video if you want to catch up. Not all the way, you can stop at polonium and, oof. Oh my goodness, I'm putting myself to shame. Anyways, from PO and AT, staircase pin there. Anything lower than that, it starts to get a little muddled. And I'll explain to you in just a bit, but all we have to do is the staircase. This staircase is essentially what divides this periodic table into 2 halves. On the left side, we have metals. On the right side, we have non-metals. On the left side, being metals, they are typically fairly lustrous. You know, they conduct electricity, most of them, okay, most of the time. They conduct heat most of the time. They are malleable most of the time. So there's a general trend you see on the left side of the periodic table. On the right side of the periodic table, they are called nonmetals. And they couldn't be any more different than the metals. In fact, they are usually liquids or gas. They are not very conductive usually. What are some other things we know about nonmetals? And just a whole bunch of stuff. And so, be that as it may, we are going to separate the left side and the right side of the periodic table as metals and nonmetals. And at this point, you might ask, well, what about that staircase? The staircase is where where the metals and the non-metals meet. There's a bit of a, I don't want to be unscientific, but there's a bit of like a meld. There's a bit of a fusion where a lot of these elements show little bits of properties of both metals and non-metals. And because of that, we give this section a name called metalloids, which has, I'm going to write properties of metals and non-metals together. Properties of metals plus non-metals. Which ones exactly? Well, almost every single element that is touching that staircase. In fact, every element that's touching the staircase except aluminum. So starting with boron, and silicon, then germanium and acetine, Sn is tin, Sb is antimony. Oh man, I really need to refresh mine. I've been away from grade 12 chemistry for too long. Okay, and there it is. I can't really see it much, so how about I color a little again? Orange, so you see it better. Okay, so this is the staircase for metalloids, and these specific ones show properties of both metals and non-metals. So there are some names that you can keep with you. Metals on the left side, non-metals on the right side, metalloids on the staircase. And of course, it wouldn't make sense to just leave it as that. If you're going to give these general names, we should also have some specific names too for columns because they behave similarly. I'm going to introduce 4. There's a family name given to group 1 and 2 and 17, 18. Group 1, the family name for group 1 is the alkali metals. Right? They're pretty special. And if you remember my demonstration, I threw lithium, potassium, sodium, and potassium, and they all behave vigorously. Potassium more so than lithium, obviously, as we go down. But they all behave in a similar manner with water, and so they are called alkali metals. Group 2 are given the name alkaline earth metals. And they also behave relatively similarly with everything around them. Let's see. Group 17, let's see if I could squeeze this here. Group 17 are the halogens, like halogen lights. And noble gases is the last one. I know that sounds a little funny. Noble gases, they're actually really unreactive. You could think about noble gases. Maybe the name came from actually personifying nobility. If you think about those like old school genres of aristocracy, sorry, where there's commoners and then there's nobles and there's royalty, right? And the nobles are like all pompous and cocky, and they're like, commoners, they shouldn't stay with us because we're special and you're not. So they don't really like to associate with others. So noble gases don't really react. I don't know whether that's why they call them noble gases. I don't know. But because they're not very reactive, there's some really good uses for them. Like neon, you might recognize neon as neon lights. Even if we zap it with electricity and give it a lot of energy, it's not as volatile, it's not going to explode. And so there's some uses for the fact that they are not very conductive or not very reactive. So this is my periodic table. I would like everyone to, including you, be familiar with periods. Here's a recap. Periods, groups, the fact that the group tells you how many electrons are in valence shell, metals on the left side, non-metals on the right side, metalloids on the staircase. We give 4 special names for columns: alkali metals, alkaline earth metals, halogens, and noble gases. And that's it. That is essentially the entire lesson. We're going to fill out this sheet, to summarize everything that we have learned in this video. And we will have a evaluation sometime in the future that covers all of this, right? So let's do this very, very quickly. So focus. All right. Starting at the top and reading left to right, the elements are organized by increasing atomic number. Starting from how many elements are there? 1 to 118. Elements are organized by increasing atomic number. This means the elements are also organized by the number of something in the nucleus. The atomic number is the same as the number of protons in the nucleus. Elements with atomic numbers 1 to 92, except 43, are naturally found on Earth. Fun fact. Symbols indicates the identity of the element. First letter is always capital. If you give me, for example, sodium is Na. If you write Na or capital N, capital A, both are incorrect. Please remember that. Practice. What's the name of the element represented with the symbol K? Going once, going twice. Potassium. Okay. You might wonder, why is potassium that says with a P given the letter K? Well, all these symbols in the periodic table are actually, they refer to their Greek Latin words, names. So for example, sodium for us is salt, sodium, but it's given Na. The original name for sodium is natrium or natrium, and that's why it's Na. Actually, a fun fact, my dad didn't know what sodium was, but when I told him it was Na, he's like, oh, natrium. I'm like, how do you know that? Apparently back in Korea, he learned based on the original names, because whether it's Greek, Latin, or English, it's still a third language or a second language to Korea. So in science class, he learned that as natrium, not sodium. Interesting. Some other ones that are sort of funny. So that's copper, Cu, that sort of makes sense, I guess, sort of. Cu is not Co. Cobalt is Co. Copper is actually cuprum. Fe is iron. Why is it not Ir? It's because iron in the original language is ferrum. Gold, Au, aurum, some other ones. Iron, sorry, lead. You know, the poisonous metal? Lead is Pb, because in the original language, it's plumbum. You know, a lot of weird things. Okay, so it's from the most part, the letters do match the first letter of their names, but not always. Atomic mass. The periodic table shows the something mass of all known isotopes of an element. The periodic table actually shows the weighted average mass. You learned that more in grade 11. And you might not have heard of the word isotope. You don't have to worry about that. We will have a lesson on this in the next class. But since this is a bit of a summary table, I thought I'd throw it in there anyways. Atomic mass represents the mass of one atom of an element. Atomic mass generally increases with atomic number. This is true. Metals, metalloids, or nonmetals. Metals are usually elements with a high luster, malleability, solid, not sold, solid, at room temperature, conductive, and are found on the left side of the periodic table. Nonmetals are usually low in luster, brittle, gas, liquid temperature, non-conductive, and are found on the right side of the periodic table. Metalloids have properties of both metals and nonmetals, are found between, like a staircase. Okay. So it's, it says draw the staircase on your periodic table to separate the elements into metals. We did that. Is nitrogen a metal, metalloid, or non-metal? So going back, nitrogen is right here. It is not touching the staircase. It is a non-metal. Okay. You might want to pause and just try to catch up. When you're ready, turn the page. All right, let's finish this last one. Let's see. Families are groups of elements. So again, remember families are the columns. We have 4 different family names. Families are groups of elements with similar chemical and physical properties due to the, what do we say? Coincidentally, right? The number of electrons in its outermost occupied shell. The outermost occupied shell is called the valence shell. And of course, remember the electrons in the valence shell are called valence electrons. Right, so creative. Anyways, family names. Some things that you might pick up along the way are some properties of these family names. Some examples: alkali metals. You know that they are very reactive. That's my short form for reactive. Sorry, this is how I survived university, by making up weird shorthand. So this is reactive, and I think they're not bad. I think it's pretty good, right? So if you want to adopt it, you can. They're really reactive with water or H2O. You see that often, they're shiny and lustrous. If you remember from my demonstration, they're usually sort of soft. I was able to cut through alkali metals like butter with a knife. They often have low melting points and boiling points, and so forth. Alkaline earth metals, they're not necessarily as reactive with water. Some do, but they definitely are less reactive. Alkaline metals, though, just to continue the pattern, I'm just going to say they're very reactive with acid. Okay? And they are not as soft, but they're still shiny. They're sort of silvery and blah, 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 just like other metals. Halogens, they're not very good conductors. Neither of them are very good conductors. I'll just say for halogens, maybe just low melting point, boiling point, because they're gases and whatnot usually. Noble gases is where I will say they're not very reactive. Oh, this one is. Okay, so they are very reactive and not very reactive. They're usually gases. They exist as a single atom. There's so many different things I could write about this. Let me just add one more here. Exists as single atom. Okay, they just sort of float around on their own. They don't like to bond or make molecules with other things. So these are some properties, and that's why they are given family names. They behave so similar to each other. Let's move on. Period, aka the rows, right? The period that an element is found represents the number of shells in the atom. How many shells are found in an atom of calcium? Well, calcium being Ca. If you go here, calcium is found on the 4th period. Bam, already you know that there's going to be 4 shells. Okay, it's in the 4th period. What about, I don't know, there's another one. What about fluorine? Fluorine, Fluorine is here. It is a 2nd row. Gonna have 2 shells. All right, that's how you know. Group, aka columns. The group that an element is found is related to the number of electrons in the valence shell. If you remember, if you were in group number 2, you had 2 valence shells. If you were in group number 18, take away the I guess a tens digit, and you would have 8. Okay. Practice. How many valence electrons are in an atom of lithium? Lithium is group number 1. Therefore, 1 electron, 1 valence electron. How many are in oxygen? Well, oxygen is here. It's group 16, but we focus on the ones digit. There's 6. valence electrons. And that's it. We took the time in the rest of class to work on your Bohr-Rutherford diagram assignment. If you don't remember, I'm going to have to ask you to go back to this sheet from our lessons, where you learned how to draw the Bohr-Rutherford diagram, and then practiced it together, and then ask you to follow the same electron arrangement to fill in this. The very last sheet of that package has a set of questions that are worth 8K, 6A, and 3T all together. So go through each of these and see if you can answer accordingly. For numbers 7, 8, and 9, you might be a little confused of what I'm trying to ask. They are all worth only one mark. I'm asking you, what could you say? What are some things you can say about an atom if it gained another proton? Okay, what happens when the number of protons in an atom changes? So this is just an example. I don't mean hydrogen plus 1. You could use that as an example, but like it could be lithium plus 1. It could be sodium plus 1. It doesn't matter. What happens if I were to shove an extra proton inside the nucleus? What happens? Same thing. What happens when the number of neutrons in the atom changes? For example, what if I add 2 neutrons into carbon? What could you say about this new atom here? And lastly, what would happen when the number of electrons in the atom changes? What can you say about an atom if I lost an electron or I gained an electron? There it is. Okay. Please complete this. This is supposed to be due on the Monday when you return. Okay, a handful of students got most of this done during the class time, and some of them actually handed it in because they felt confident in their answers. So it shouldn't take you too long. Your homework for that Monday, as well as this, is to have something to show me for your science fair. That means give me show me a video, like a 5-second video of you doing something for your lab. 2, some pictures. 1 or 2 pictures of you, 2, 3, 4, whatever, more than one picture of you actually doing the lab, or a picture of your lab setup. That's sufficient. 3, please write me. By now, you should have for me a formal write-up of your procedure. Formally, so in other words, third person past tense, what are the instructions or what happened for you to set up this lab? Okay. And number 4, preliminary data. It doesn't mean your lab has to be finished. I just want just some set of data, your first numbers. If you're growing plants, like tell me how far your plants have grown so far. If you are, measuring salt content for something or seeing how quickly something dissolves, I'm hoping you had a chance to do at least one trial so you have some numbers to show me. Okay, hope this is good. Work hard, and I will see you in a week and a bit.